previously, we can reference that later. Yeah, so you need to click that the recording button, yeah, on your side as well. Yeah, okay, so previously we have already had 7 series of that in the presentations. Yeah, we introduced that in how to write in the scientific of the papers, how to publish that in the high quality of the journal. Then after that, yeah, so I introduced our recent work using the GPGPU-HFDEM, mainly focused on the development. Then after that, I introduced a few of the examples. So from there, I have already given 4 of the tutorial, yeah, about that, how to use our code to model the values of the static of the problem. So which will include the Unix complex test and the resilience test. Yeah, so that is the traditional of the rock mechanics test. So now I wanted to focus on that's the more state of the art, the dynamic test. I think here at this moment, the dynamic test actually is the focus at this moment. Okay, I will show that using obviously for the rock dynamics, so they have many kind of that test. You can have that in the drop of the test, you have that in the rock blasting of the test. Yeah, but the widely adopted one for the dynamic test in the laboratory using the split-Hopkinson pressure bar. Okay, so then this is the focus of the today the tutorial is that how to build an SHPB based the dynamic BTS3D, so using the HFDEM developed by ourselves. Yeah, I think that some of you may have already attended this the recent conference, which is hosted in China. So that's the Rock Dynamics 4. I think that's a few of Marcus' team attended this conference. And I think that's a few of you, yes, participate in the organization of this conference as well. Yeah, I can see from that website, Mark is that in the organization of the committee. Yeah, so on that conference, we presented in a paper as well. Yeah, so that's written by my former of the PhD students. Yeah, we have here that's collaborating with the Monash University. So we using our code to model their unique of 3-dimensional of a Hopkinson's bar. Yeah, it's said that's the only of the equipment, yeah, available all around the world. Yeah, and recently in Shenzhen University, so they construct another of that the triaxial Hopkinson's pressure bar. Yeah, using that the differently impact of the mechanism. Okay, so for the presentation, actually is mentioned by the second also. So that's our presentation is mentioned by Daisuke Hokuda. Yeah, I think that he also delivered a presentation for both of the rock dynamics committee for Chinese rock mechanics and the rock engineering society, and also for that's the rock dynamics committee for the International Society of the Rock Mechanics, and that's the mining science. Yeah, so here's that's in the second also, the first also, that's the form of the PhD student. Then we have that's in the another of that's in PhD student from Monash University. Yes, and then me as that's the Chris Mandler also. Yes, and then Tian Bing, that's famous of the researcher from Monash University working on the rock dynamics. I think that's in the next of the rock dynamics conference. I think that is scheduled in 2024. Okay, so that were hosted by Tian Bing, that's in the Monash University. Okay, let's come back into this topic. Okay, what we building here today, so we building that's the one-dimensional, or that's called the conventional, traditional of the split-Hopkinson impressions bar, instead of that the mostly state of the art of the three-dimensional split-Hopkinson impressions bar. Okay, for you to build in this system, you firstly need to understand the laboratory system. Okay, in the laboratory, the split-Hopkinson pressure bar test system, so which is consistent like this. Okay, here you have a gas gun, which will provide an impact. Okay, so that's the impact of the bar. So then the impact bar impacted the incident bar. Then that's where generating a stress wave. The stress wave which will propagate in the incident bar. So then we have that in the rock samples here. Then on the right-hand side of the rock sample, so you have that in the transmissions bar. Okay, so the stress wave which we're transmitting along the transmission bar, but actually some of that which we're reflecting back, which will come back into the incidence bar. I think that's in the split-Hopkinson pressure bar testing system. So now, even that's in the modern of the rock mechanics laboratory, so this is regarded as the comprehensive the laboratory testing that equipment. Yeah, so no, I think that's many of the universities have this equipment. No, that's like that's Northeast University. Yeah, I visited there. So now I have that the split-Hopkinson bar pressure system. I'm not sure whether we have that in Daniel University of that technology. Okay, so here. Yeah, so for the dynamic test, which happens that's very fast. So then fast to monitor of that the failure process of the rock sample, we need to use the high-speed camera. So here that's usually putting that in the high-speed of the cameras there. Okay, then for the incident bar and that's the transmitter bar, for us to trace the stress and wave propagation. So then in that case, so you were putting that in the monitoring of the point there. Okay, usually we put in that in a strain gauge. So here that's in the incident bar, and then we were putting another of strain gauge in the transmissions bar. Okay, so this is that what is usually we do that's in the laboratory. Okay, for our case, we were building that in the full of the system. Instead of that, if you read in that in the literature, some of that in the literature, even so they claim that they building that in the SHPB based in the dynamic test, but what they consider, they only building that in the rock specimen. So then they put in an impact at here, so on the rock specimen. For our case, so we were representing the full of the laboratory system, so including the incident bar, the rock sample, the transmissions bar. Yeah, obviously, so I will ignore that's the gas gun, and then the impact bar, I will put in that in impact. So here, I did the start of that in the incident bar. Yeah, obviously for this case, since we put in the full of that in the system, so here, you will need to build in a big of the border involving a large number of the elements. So then in that case, yeah, so for the non-parallelized of FDEM, so that's where be struggling. So even if you using that in the CPU based the parallelizations of the skin, so you need to using the super of the computations as well. So like into this, so the Los Alamos National Laboratory, so in USA, so they did that using that in the CPU based the parallelization of FDEM modeling this. So they're using a computer which is have I think that if I remember correctly, is have that 183 of that the CPUs. Okay, for our case, we were only using single of the CPU, and we were using usual of that the desktop instead of using the super of the computer. Yeah, but obviously, so we have that a good of the graphic card. I think for this modeling, so you have the graphic card like GP100. So GP100 is that about 5 years ago. So that's the state of the art of the GPU. But now, yeah, actually, so GPU is already obsolete. So we have much better of that than the GPU available. So that's today. Yeah, and another one is that while we are able to use the personal of the computation to model that, so we implemented that in our self-developed version that's called the adaptive contact activation, and that's semi-adaptive of the contact activation. So then in that case, which is a contrast, that's which called the BCAA, which is called the brutal contact activation approach. Yeah, for other of the group, they're using the brutal contact activation approach. So for their case, their computational cost is much more intensive. Okay, so for this one, we build that in the numeric models like this. You can see we have that in the model that's in the input bar, and that's in the transmissions bar. Then we have the rock sample. Yeah. So if I zoom that part, so that's a rock sample is looks like this. So for the rock sample, we using the very fine of the meshes. For the bar, since the bar only have the elastic deformation, then in that case, we using that rather close of that mesh. Then at the end of the input bar, so then we given a dynamic impact there. Okay, then here that's the burden results in selecting this. Okay, I show you that's in the video. Okay, you will see that's the impact on this side. Then you will see the stress wave, which is propagate and then reflecting back. So then you have that in the rock sample. So that's the field. Okay, as I said, we will install the strain gauge in the incident bar and the strain gauge in the transmission bar. So then in that case, you can trace, monitor, so what is the stress wave propagation in the input bar, in the incident bar and the transmission bar. Okay, so then you can use the Excel to draw the data. Okay, I will show you how we get in this kind of data. Then we draw that using Excel. And you can compare with that the experimental of the results. Okay, so like that. Yeah, so we compare that with a test which is completed by Monash University. So you can see that's the stress wave, either in terms of the incident stress wave or the transmission of the stress wave, which is correspondingly very well. And we have much less of the noise compared with the cases, so the experimental of that the test. And for the pattern, so which is generally consistent as well, although for the fragment, it depends on the heterogeneity of the sample. So you will see that the fragmentally along that the central line is different. But for the pattern, for both of the case, so you can see that's along that's the center of the line. Okay, so this is that's the task which we will do today. So using that in the SHPB. Yeah, obviously, so this is that's one dimension of that in the HPB. Yeah, so here, if we slightly to change it, the other of the laboratory test equipment or that's the numeric modeling, so you will notice we will be able to do a series of that in SHPB based the dynamic test. Okay, so here, another one is that suppose we change that in the sample. So all of that in the order of the locations that's in the same. We only making that in the sample. We using a cylinder of the sample as what we do. That's in the laboratory, the unit axis complex of taste. So then here, so we can get in that in the dynamic unit axis complex of taste as well. Okay, so I'll show you a video. We put in an impact here, then the stress wave propagate. You can see when the stress wave propagates, so that's causing the macro damage of the sample. So then when the stress wave propagate, then the sample which is highly loaded, yeah, the stress. Okay, then after that it's passing through, then you will see that the sample which is starting to failure. Okay, unlike that for the static unit act complex of test, so you may observe that the single of the split failure or that's the shear failure. So you can see for the dynamic of the unit act complex of test, which is resulting the complicated, so the failure pattern. And there's a rock sample, so which is fragmented into many of the fragments. Okay, so this is one, we only change it. So we using that in the center of the model, we only change that in the sample. And then the other one, which we usually do, that's in the laboratory, so which is called the spawning. So in the previous case for the rock sample, on the other side, we have a transmission bar. Here, suppose we do not have that transmission bar. Instead, we put in that in a cylinder of the rock samples there. Then in that case, when you put in an impact here, then the stress will propagate. When the stress will propagate in here, which will reflect back, which will form a tension of the stress wave. Okay, the tension stress wave, we know the rock strength. So we have the tension strength, which is much lower than the compressive strength. So then, which will cause this kind of spalling of that the behavior. So that's what we usually observe that in the dynamic testing of the in the laboratory. And here is that need modeling. Okay, the other one is that I showed you that before. If we change this sample, we make this sample is a notch of the sample. So then we can easily to do that in the dynamic of the three-pointedly bending of the test. Okay, so here, yeah, like that in the paper which we presented in the rock dynamics of the conference, rock dynamic 4. Yes, I mentioned that in a few of you. I think that's from that's in the conference schedule. And I think that's in Zhenhu, Zhiyi, and Mark. Yeah, so you should have already attended that in the conference. Okay, over that's what we presented. We put in that in the a three-dimensional split-Hopkinson bar. You can see, so what we do that in the previously, you already have one-dimensional. Then here, you have the confinement in this direction and the confinement in this direction. So if we look at that in the around the sample, which looks like this, okay, we build in that in the numeric model, so using the HFDEM of that in the software. Then the samples there, so that's the cubic of the sample, unlike for the previously. For the we have the symmetric of that in the sample. And here we use a huge number of that in the elements. Yeah, either of that in the cohesive element or that in the solid of the elements. Yeah, you can see here we have 2.5 million of the nodes. So 1.2 million of the cohesive element, and that's 0.8 million of the tetrahedral element. That's a huge number of that element. But we can still be able to complete that in a personal computer. It's unnecessary for us to use in high performance computer. Okay, so here, so for this, the confound of the dynamic test. So what we do, we have this actually, which is called the combined static and the dynamic test. Okay, so the static test, which is initially we apply a confinement on the sample. So after we have that confinement, so then we give an impact into here. Okay, so this is that in the modern results. You can see we put in the impact here. Okay, this is consider that's the one dimension of the cases. Only of the difference here, you notice that in the previously, what we use in there, which is the circular bar. Here, this is actually which is square of the bar. So you can see represent result in the complicated the failure of the pattern. And the other is that compared of the stress wave propagation in that's in the incident bar and that's in the transmissions bar. And here, this is that show another of the word. This only show the rock sample. So here, this is the confirmed case. So we have this direction. We given a confirmed which is 30 megapascal. Okay, so this is that we apply this load, which is through the static of the process. And here, in the left and the right hand side, so we apply that's 10 of the megapascal. Then after that, we give you an impact here. So then you will see here, that's in the rock sample. Due to that's in the confirmed here, which is causing the spalling of that in the behavior. Okay, we also model that in for the three-dimensional of the confirmed case, which is compared with that in the laboratory experimental and that's in the numeric modeling. Okay, what I introduced in here, so this is that we have that in the extension of that in the SHPB. We either by changing the split-Hopkinson bar or changing the rock sample. Then for the same model, it's easy for you to do order of that in the model. So then that's why I say the tree which I introduced in here today, that's for one-dimensional split-Hopkinson bar dynamic of the BTS testing. So it's easy for you to extend that into the order of the modeling. Okay, then we already given an overview of that split-Hopkinson bar based on the dynamic of BT test. Okay, so now let me introduce that and how we do that. Okay, how we do that? I have another example which will show further making that complicated. So when I given this in the sample, which is considered this is grain-based. Unlike for the previous case, we consider that's the homogeneous of the sample. In this case, I have that in the grain. And each of the grain, actually, I can control. So that's the intergranular of the crack, or that's the transgranular of the crack, or the intragranular of that in the crack. So you will see that's in the failure pattern, so which is different. Okay, so here this is another of that model, which is the same of that in the previous of the biaxial of the compression modeling. Only of that in the difference I have that in the sample here. So this is a grain-based model. And here I deliberately to put in that in the intergranular of the cohesive element to become the weak of the element. So you will see many of that during the failure, which is retain of the grain of the shape. That is that I put in that in the between of the grains. I put in that in the weaker of the cohesive element there. Yeah, so during the body, you can control whether you need to put in that in the strong or weaker of that's in the intergranular or that's in the intragranular of the cohesive element, then makes that modeling. So that's very flexible. Okay, so for the modeling, a model which is at this scale, so it won't really work if we using the GUR version. So we were using that in the HPC version, so we do not have that in the graphical interface. When you run that, So you were only getting that an interface selection. Then you give a lane, then given that an input parameter, so that's wrong. As I introduced that before, so we have that in a few of that in the version of the software. So that's a GUI Windows version and that's a Linux version. So here for the split-Hopkinson bar based on the dynamic test, so you will only be able to use these two versions and should not use the graph using the interface of the version, since that one which were involved to deal with the graphics, making that the calculation is very slow. Okay, so first to do the modeling, which is the same of the step as what we introduced before. We firstly need to build in the geometric model, then we build in the Bayesian model, then we give the boundary and the loading condition, then given the material property, then given the control parameter. Yeah, I think that's for all of the previous tutorial. So I already focused on building the geometry and there is a mesh boundary condition and the material model. But I didn't introduce for the control of the parameters. So this is that the focus of that today. So today I will focus on that how we control the running of that in the software. Okay, then for the building geometry, the mesh model, the boundary condition, and that material, I will quickly go through. Yeah, obviously. So the first step for us to building this is that to building the geometric model and the mesh model. So I mentioned that before. Yeah, so our software is that no, we will focus on the calculation. We do not do the pre-processor, do not do the post-processor. Yeah, so for the GUI version, we do a little bit pre-processor and a little bit post-processor. But for the HPC version, so we do not do the pre-processor, post-processor. So pre-processor and post-processor, we use the third part of the software, either that's in the open source or that's in the commercial of the software. Yeah, as I introduced them before, for the pre-processor, you can use the oracles and the ANSYS or using Solomon or using that in the Gmesh. Okay, so here, the first step, which is for you to build in the model. Okay, so the same as the previous, since this is not related to our software, which is the standard of the finite element software. So I have already built in this model using our course. Yeah, then I will not introduce that how we build in this model. So I will show you that how this model was transferred to our model. Okay, so as what we reviewed that previously for the split-Hopkinson bar based on the dynamic BTS3D. So you have that in the input incident bar, the transmissions bar, and that's in the reactance sample. And here, so we need to build in the geometric model and a mesh model for all of them. So this is easy for you to do that using commercial software like in Abacus or that's in the open source software. So that's in the Solomon. Okay, so here, if let's look at that a little bit closer of that in the mesh. Yeah, since we focus on that in the failure, which is in the rock sample, and for the split-Hopkinson bar, we assume that have the elastic behavior. There is no point for us to use the density of the element there. So we only use the density element for the rock sample. But you need to be careful. So all around that's in the rock sample. That's where involving the interaction between the rock sample and that's in the SHPB bar. Okay, for that in the pressure bar, then in that case, to make that in the contact accurately to calculate the contact interaction, then in that case, at the end of that in the pressure bar, so suggest you to use the fan of the element. Ideally, so this at least the loss layer, which will as fine as that's in the rock sample. Okay, so this is that in which will show that in the palm hunter presentation. Then let me show you that in the model which is built in here, the data file. Okay, I have already prepared this in the input file. So as that's for all of the previous of the tutorial. So after this presentation, I will share this all of the data file. I will upload that onto Tintin's computer. Then for you can access Tintin's computer to get into that. Okay, so here this is that what I built in that in the abacus. Okay, so this is that in the model. Okay, I show you that. Okay, so this is that in the RMP file. So in abacus, after you build in the geometric model animations that you can output in that in the RMP file. RMP file. So that's what we need is that. Okay, so let me show you that. Yeah, so let me open that up because I already put in that. Okay, let me get rid of this one. So I build in a new of that in the model. Okay, so let's input in the file, which is already generate. So we go into file, input. Okay, input in that in the model. Okay, so that model, yeah, so that's the RMP file. Okay, I click into this one. So it's take a while. Okay, so here I needed to mention that I was stressing that before, later. So at this point, you can see we put in that in the origin. Yeah, here we given that limitations that here, the origin. Okay, let me zoom this up. Yeah, so for origin, yeah, we put in that. Yeah, so the origin is that in the contact surface between the rock sample and that's an incident bar. And for the incident bar, we put in that along, okay, see here, this is along y-axis. And this is all of that's in the y-coordinate of the incident bar, which is smaller than 0. And then for the transmission bar, which is that's bigger than 0. Okay, so this is that's in the data file. So we say for this data file, which were included in the information which we needed. Okay, so let me close into the order of that in the input and file. Okay, so let me move in this to another of the screen. Okay, let's look in that in the format of this input and file. Okay, I already showed a few of that in the example, 4 examples before. So looking that instruct you how do you look in that in the structure of this data file. Okay, look at that. So we have here that's the inclusion in 2 parts, and one part is that's for the rock sample, and the other one, which is for the pressures bar. Okay, for each of the parts, so you look at that in which we include in the node, and that's in the element. And for the second of the parts, you can see that's again, that's including the nodes and the parts and the element. Okay, so this is that information which we want. Okay, we say as we introduced before, first to use the HFDEM, we need to provide 2 input file. Okay, one of that's the input file, which is the element, and that's the node of that information. Okay, so here we copy the data, which is from Opcos MP file. So copying that file, you can see that we copying that in the element information, and that's the node of that the information. Okay, here I have already introduced that 4 times in my previous 4 presentation. Okay, so this time, so I will not introduce this detail since I have already introduced the many of the time. And here you will notice that for me, either I do that in the static of that in UCS BTS or the dynamic. So UCS BTS, I use that in the same of that in the Using that in the input file have the same of the format. Okay, let me quickly go through that. Suppose if you missed any of format of the presentation. Okay, the first one, that's the total number of the elements, total number of the nodes. So here, this is that's the nodes and the element in each of the parts we adding together. So that's called the total. Okay, so then we say we have two parts. Then we given the first part in the lane. For the first part, okay, so what is that in the number of the element? The number of the nodes. Okay, then that's the translation, rotation. Okay, then that's the element connectivity. So then that's the node coordinate. So that's almost that for any of the numeric modeling, or that's specifically all of the finite element modeling. So you will have the data structure, which looks like this. Okay, so then after that, we have the second part. The second part, we using that to represent the SHPB, the split-Hopkinson suppressions bar. Okay, again, so you will have this and that and the number of the nodes, number of the elements, number of the nodes. Okay, then you will have the element connectivity. Okay, so then that's the nodes. Okay, so then the remaining, so velocity, the remaining here, as I introduced that before, for this section, I will using that in the script. Okay, so that's in script. Yeah, I prepared that in here. Actually, so that's almost the same as what we used in that in the before. Yeah, I have this and that, and each time I slightly changing. Okay, I already shared this, the previous, this four of that in the file, so that's with you. Okay, for me to do this, SHPB basically the dynamic use a BTS test. Actually, I slightly to change this. Okay, then I relearn this one. Okay, where is that in the change for the previous one? So the change is that in here. As I mentioned that before, here, this is a simple of the C++ program. So you need to understand this one. Okay, so let me, close. This solution, let me open that in solution. Okay, so this one, which is I save that in OneDrive. Okay, so that's here. Okay, to generate that part of that in the data. So I using that in a C++ program. Okay, so let's look into that in the C++ program. Yeah, so here I have already showed that a few times of this and that in C++ program. Okay, so let's look at that. And so firstly, we do that in three-dimensional modeling. Yeah, so here you have that in one. Okay, that we go back into the beginning of that in the input file. Okay, so then we have the total number of the elements. Then the total number of the nodes, which is this one. Okay, so here, what we do, we were given that, okay, I have that in here. Before that, I have this in the PowerPoint presentation. Okay, so for this, for this disk, so that's represented the rock. We needed to give the material properties given that's in the rock. Okay, what do? We have that in the rock, we label that as 0. And then for the incident bar and that transmission bar, we label that as 1. Okay, how we do that? So that's we through this. So you can see here, okay, for the rock, okay, so let me come back into here. Yeah, for the rock, we will have the element. Okay, the element, the maximum number of the element, which is 179,260. Okay, if I have that in the elementary number which is smaller than this number. So then that means this is that's the elementary for the rock. So then I given a label. I given that's a label that's 0. Otherwise, if that's bigger than this one, then I given that 1 represented that's this is the split-Hopkinson pressure bar, the nature. So I will given that the input parameter. So that's the steer of that input parameter. Yeah, so here that's we introduced before. 0 and 1, which is represented that's the materials here. So as we introduced the velocity time, so here we have the first column that's 0, then that's the column that's 1. Okay, you look into that. Okay, previously we already introduced that how we given this parameter. Okay, for you to easily to spot that, okay, we have that in the rock. We know that's the density, which is around 2.36. Okay, here we have this that's a marble. A marble is a little bit heavy, so we have that's the density, which is 2,800 kilograms per cubic meter. Okay, then for the steel, we know that's in steel, most of that which is 78. Okay, so this kind of steel, we have that's in 7,697 kilograms per cubic meter. Okay, all of that in the other parameter we introduced in that since before. Okay, this is that given the material property. Then the other one, we needed to give that in the boundary condition. Okay, for the boundary condition, what we given, we're given that in the boundary conditions, that's here. Okay, for the boundary condition, so we have, let me clean my computer screen, making this become smaller. Okay, on this set, so we were inputting an impact. Okay, we were given an impact on this set. Okay, when I apply that impact here, so I will making this fixed so that impact that I will only have this stress wave which is transmit, and here that does not have that movement. Then all of the other location is unnecessary for me to fix anything. So I can make that in the free. Okay, then in that case, yeah, I only select so this part, making that which I will apply that in the boundary conditions there, and all of the other location I will give that 0. Okay, so this is that what we do. Okay, let me clean my computer screen. Okay, so this is that what we do, that's here. So you look into that, okay, we come back into here. The next one, what we do is that we initially given that all of that in the node of the property, we given that in 0. Okay, so this 0, which we're corresponding. So later we have the given that in the boundary conditions here. Okay, we have this row, the coordinate of 0, then this coordinate of that is 1. Okay, 0, so you notice that actually we didn't give any of that confinement here. Okay, you look into that into here. Yeah, we have that in the boundary condition, either x direction, y direction, z direction. So we have that 0, 0 means that's free. Okay, then we have that at the end here. We given that 3. 3 is given a displacement. But for the displacement,
sorry, the screen is static at the previous image. So
really? So the screen is plus did it. Okay, let me stop and that, and then I share my screen since again. Yeah, so
yeah,
can you see my screens now?
Yeah, yeah.
Oh, great. Yeah, sorry. Yeah, I didn't know. Maybe so.
Please
that's
continue. I'm sorry to interrupt you.
Yeah, no worries. So sorry. Maybe that's due to Zoom of the problem. Okay, so let me come back into here. Okay, we say we were given the boundary condition. So for all of the other locations, we do not need to give any of the boundary conditions here. The only place we were needed to give the boundary condition is that, yeah, we needed to put in an input of that's in the wave that's in here. Okay, what I do is that I fix, so that's the boundary. So actually it's not fixed, I give you a displacement boundary. So displacement, actually we have this related to that time. Displacement divided the time. Actually, what I give you a velocity of the boundary, that's here. Okay, the velocity, so which were related to that's the impact. Okay, this impact I will introduce that in the later. Okay, anyway, at this moment, I label this part as 0, as 1, and then any of that in the other part, what is given that in the 0. Okay, how we do that? We do that since, which is quite easy if we using the script. So using this script, okay, I have that in the script that's in here. So I firstly, given all of the node are given that 0. So that means I will have that in the free everywhere. Only have one of that in the location. Okay, so I have that in this location, I will given that is 1. Yeah, obviously, so for that one, if you wanted to identify that boundary by hand, that's terrible. But in the Abacus, or that's in any of that in the order of the software, actually you can create the set. Okay, so I show you that I already created that in the settings here. Okay, let me show that in the visualization. Yeah, I have that in the sets here. So the sets, yeah, I will have that represented boundary. Okay, if I highlight this one, so you will notice that. Let me zoom this part. Okay, so you will see. Okay, let me show that in the transparent. You can see here, I define a set for all of the nodes, which is at the end of the incidence bar. And here, that's I already demonstrated how you do that in articles that before. It's very easy for you to define that in the set. So then you can extract that. Okay, what I extract in this in the notes is that when I create a job, then I write in the input file. Okay, then the input file, which will be, okay, so let me show you that in the input file. So the input file, I have that defined of the sets in there. Okay, so that's the set which I defined here. Okay, so for that one, the lately, so when I define that set, which will give me all of that in the load of the number, and that's in the loading number, then in this C++ program, so I read into that part. You can see, yeah, I read into that. Okay, so let me show you. As that's what I introduced in that in the before. So we copy that kind of information. Then we put in that. Okay, so that's an input. Okay, here, this is that. So what I do is that I use this C++ program. So I reading this, you can see first I reading the keywords. It can be any of the keywords for convenience. So then I reading this, what is that in the total numbers here. Then in the opcos, as I mentioned that before, so you will have the output, always each line have 16 of the number. Then you can see I reading 16 of the number. After 16, then I reading that in the next line. So after reading that, yeah, since here that's a C++, I have that in the index, which is starting from 0. So that's why I minus 1 here. And then the other one, that's I add the total number of that's in the rock sample. Yeah, that's because in Abacus, so we have each of the parts. Okay, we have here, we have that's in 2 of the parts, one part which is represented the rock sample, and then the other part which is represented the SHPB bar. In opticals, so each of the parts which is separately numbering. But for our code, we have that which is continuous numbering. So that's firstly starting from 1 till that's the maximum number of the rock sample. Then it is the maximum number, then I continuously labeling. So that's why. So here we add in that the total number of the rock sample. Okay, so then here we given that 1. Then this we're giving us the boundary condition. Okay, for this test, it's unnecessary for us to give the order of the boundary condition. So that's all the boundary condition which we needed to give. Okay, so after we given that the boundary condition, the next one, we needed to have tell the program initial of the contact. Okay, we know that's the initial of the contact. Initially, before that, the failure, you will only have the contact at the transmission surface and the rocket surface. And here, sorry, that's the incident bar, the contact surface between the incident bar and the rock sample, and the contact surface between the transmission bar and the rock sample. And here you will have the initial of the contact. Okay, here the initial contact are given that through a flag. Okay, for all of the other of the location are given a flag of 0, and here that's 0. And here the inside are given 0. Only that's in the edit boundary, so I given a flag which is equal to 1. Okay, how we given that? Again, so I using that in the opticals to define the set. Okay, I already defined that in the set into here. So you look into that. The set. Okay, I have that in the, let me visualize and say this. Okay, you can see here, we initially have the contact in here. So I define that set. Okay, so this is that in the rock sample on the initial bar of the set. Then in the transmissions bar of the set, I define this set. Okay, then for the incident bar, yeah, I selected the load center here. Then for the transmissions bar, I select that in the load center here. Okay, after you define this set, when you output in that in the RMP file, so then you will be able to get in that in the settings there. Okay, I copy that in the set. Yeah, I put in that into here. Okay, what I give here, this is that keywords. A keyword actually can be have that any of the lane, just for your convenience of that understanding. Then, which is how many of that the number of the nodes here. Okay, as I mentioned that before, if you have a lot of the nodes, it's easy for you to calculate that. Okay, we can show that in an example. Yeah, we say for the opticals, the output each row, which is a 16 number. Okay, that means if we wanted to count how many of the number of the nodes in here, I only need to consider that's the row. Okay, I have that lost row, so that's 28. Okay, starting row, I have that 6. Okay, then I consider that's the starting row and the lost row. That means I need to add 1. Okay, so then means I have this 23 row of the data. Each row, I have that 16 of that data. Then I multiply 16. So then equal to 368. Okay, for this case, I have that exactly. So that's 23 of the row. For some of the cases, like the next one, so each of the row you do not have exactly 16 number, you may need to add or minus some of that number. Okay, then you can easily to get into this one. How many of the elements, how many of the nodes in this set? Okay, all of that. Then I use into this, the script, which is reading to that. Okay, you can see initially I was given a flag. everywhere I given that a flag of that 0. Okay, then I return that, and said if that's in the rock, I directly to reading that the loading number. But if that's the plate, then in that case, I need to add in the firstly of the parts so that I can make sure here this is the continuously of the numbering. Okay, after you given that a flag, okay, then we run since that, then you are getting this part of the, we output into that one. Okay, so then you are getting to this. Okay, so this is that in the velocity. Okay, so then that's the element property, loading property, the boundary of the flag. Okay, then we copy all of that in the data here. Okay, so then that's the, which is the data here. Okay, that's the data here. So that's the velocity. Initially, given the initial velocity, so that's static, do not have any of the movement. Actually, we everywhere given that in 0. Then element property, if we have the rock, we given that in 0. If that's in steel, we given that 1. Okay, the node property, if that's order of the location, we given that in 0. We only have that on the left end, we given that 1. Okay, then the boundary loading of that in the flag, this given that in the initial of the contact, all of the case we given that 0, only have that the initial of the contact, so then we given that 1. Okay, here in the lastly feature tree, I have already introduced the many of the times. Yeah, I will not spend the focus here. As I introduced that before, the label which we given that in the previously. So here, that's the corresponding label of 0, then that's label 1. Okay, this is that's the material property of the rock. Then this is the material property of that in the steel. Okay, I already introduced that previously, how we given the parameter for each of them. Then the next one, which is given the boundary condition. So that's we already label that's in the notes. Okay, so the first row, that's the column is 0, then that's 1. Okay, here that's free, and here we given a displacement the boundary, but since we have this that's the expression dynamics always related to time, so you given the displacement actually was related given your velocities so there. Okay, so then the remaining is that we in the rock we need to insert in the cohesive element. So we using the Bernoulli model. So here we already introduced that and how we given this parameter in our previous of the lectures. Okay, then here this is how we insert of the cohesive element. You can see here for the steel, we do not insert in the cohesive element. Since for the steel, we do not consider that's damage failure. We only regard that as the elastic. Only for the rock sample, we insert in the cohesive element. Okay, here this is that given how we insert the cohesive element. So here I will not introduce this detail later. I will introduce one of the model, which is the grain-based model. Okay, grain-based model, we will extensively using this part. Yeah, since here is very simple, we only insert in the cohesive element in the rock, and for the bar, either of the input bar or that's the transmission bar, we do not insert in that. Later, when we introduce the grain-based modeling, so for each of that, I will have many of the grains here, and I can control how I insert in that in the cohesive element in each of the grains. Then in that case, I will introduce this part and that into detail. Okay, so this is that we introduce that how we construct the model. Let's come back into the compounded presentation. Okay, after we given that in the model, then the next step, we were given that in the control of the parameter. Yeah, as I said, so we have two files. So one file, which is we given that's in the geometry. Okay, so let me show that's in the file. So we have two files. This file, we already introduced that this included the element node topology. And then the other one, we will control how we run this. Okay, so here, this is actually an input file. Control how that's run. I already copied that into the PowerPoint presentation. So it's unnecessary for us to come back into this file. Let's directly look at that in the PowerPoint presentation. Okay, so for the PowerPoint presentation, I think that's this one. Okay, so PowerPoint presentation. Okay, so PowerPoint presentation, so that's over here. You look at that, we have a few of the model. Okay, the first model is that here we call that the control the project dimension. But actually, so this is that initially we set in select so this. So now we include both the control of the parameters here. Okay, so here we control to do the two-dimensional body or three-dimensional body. So if you do two-dimensional body, you give that 0. So if you have three-dimensional, we give that 1. So you can look at that the explanations here. Okay, so we can control so like that we in C++ we have the array always starting from 0, 1, 2, 3, and so on. But in our case, you know, that's the node number, element number always starting from 1. Okay, so we, for the convenience, yeah, so we have back in this, if we have that 1, that means element or node, we starting from 1. If we have that given that the 0, so that means we will have the element number or the node number we starting from 0. Okay, so this is that given a control how we given that the lower bound of the array. Okay, so then the remaining, yeah, so we here you will notice later we have this code where be able to build in that in the rock blockchain. When you build in the rock blockchain, you need to consider the gas flow. Okay, so here this part which is related to the gas flow, you do not need to use this. Yeah, I ignore that part. So then the next part, so which were related to calculate the geostatic of the stress. Okay, so let me move into this. Okay, so that one which is related to calculation geostatic stress. So like that, if we model the engineer of the problem, actually model the rock burst. So before you excavation, you will have a very high of the in situ stress there. Okay, we can use this to apply the very high of the in situ stress before that's the excavation. Okay, that's not relevant to that today. I skip that one. Okay, then here, the next one is that, yeah, we put in the excavation, put in that in the previously I introduced that in the implicit and the intrinsic, or that's the extrinsic. Okay, all of that, what we using intrinsic. So that means we insert a cohesive element everywhere for the rock sample, no matter the failure will occur there or not. Okay, then we have here the order of that plan. We can consider that's the discrete inflection network. Yeah, so the gram-based modeling. Okay, here we do not use that. If you do not use that, all of that is 0. You can see both of that in here. That's 0. That means we do not use that part. Yeah, so here we can implement that in like in our FPA. We have that centrifuge, the strength reduction of that method here. We can, if you model the slope and instability, so we can consider that the strength reduction as well. Okay, here we do not consider that, we put in that equal to 0. Okay, this is that's the first, which is control of the model. One part of that is the input file, the first part. Okay, then the second part, which is control we have the explicit in the time integration as we introduced previously. We need to make sure we have the time step which is small. Like in here, I chosen the time step which is 2 nanosecond, okay, which is quite small. Yeah, previously we introduced the formula to calculate what is the step of that the time step. Okay, so then here I have many of the parameters like that whether we need to consider the gravity. For this problem, the gravity is not important. Yeah, for the computer, if we have the multiple of that in the GPU, you can specify which of that in the GPU you need to calculate that. So we using that in single of the GPU. Okay, here this is control what kind of output. Yeah, so previously like that we do the unit complex of test. We need to output the loading plate. So then we give this one. Here is unnecessary. And here we have that in the code. We can use both of the GPU calculation or that's the CPU calculation. So if you do not want to use the GPU to do the calculation, parallel calculation, so you can make that equal to 0. Okay, so here I have many of that in the order of the parameter, which is not related to here. Yeah, we using that in we proposing that in the semi-adaptive or contact activation. So we say this is much faster. And here we have values of the gain. I will not introduce into that. Okay, I will introduce in here. When we introduce in the fragment, so we notice that we have a number of the fragments there. That fragment we can actually get in the particle size distribution. So here, if you specify that one, then during the calculation, our program will automatically to calculate the particle size distribution for you. Okay, so then the remaining, that's the another of that model, which is for the interaction. Okay, here we have the values of the interactions method. So we have that's T2F, T2P. Okay, so here that's is unrelated to you. We were only using that since T2F, which means the tetrahedron element. As you know, when we have the multiple of the parts, you will have that's the contact. You can control how that's the contact. When you have the crack, which is formed, so between, if you have the crack, which becomes closer, then two sides which will contact again. Okay, so this control the different contact method. Okay, here we using that in T2F, so that's we given that in 0 here. Then the other one, which is specify what type of the material model which we will use. Okay, for the cohesive element, we were using the Mercury of that in the material model. Yeah, and here I have a number of that in the parameter like that we can control heterogeneity, like that in the RFPA. So we have an M of that value. We can use the statistical distribution. And here many of that in the parameters, so that's not related to you. I will not introduce that. When we working on this specific part, so then we will introduce that. Then for the, but for this, but I will provide to you. So this is that's in the input file. Okay, then the one here, that's important. So for this one, we only do the mechanical calculation. We only do the cracking. Yeah, so we are able to do that in the thermal conduction, the hydraulic conduction, even that in the thermal mechanical coupling, hydro-mechanical coupling, or that's in thermal hydro-mechanical coupling. Yeah, so here that's many of the parts here, especially for the thermal mechanical coupling, hydro or mechanical coupling, we are still development at this moment. Okay, for your case, we do the split-Hopkinson bar. We only do the mechanical of the calculation. It's unnecessary for us to consider the thermal, and that's in hydro. Okay, so here this is that how many of the steps which you will calculate it. So I will calculate it that 300,000 of the steps. So I will have every 15 of that 100 steps, then I will output of the data. Then here, this is that the restarting of the analysis. So that's similar to that in RFPA. When you calculated a certain of the step, okay, you need to restart in the computer. Then when you come back, so you wanted to continue starting from where you stopped to calculate it instead of to calculate it from the beginning. So that's what is this parameter. Okay, here we do not want to use in the study. We always calculate it starting from the beginning. So then we given that into 0. Okay, so this is that in the control parameter. Then the next one, which is specifically to relate it to that in the we do the split-Hopkinson bar. Okay, so here we provided 3 of the options in our code. So one of that, for the border, we do not include in the split-Hopkinson bar. And then the other one, which is sparring. So you notice that in the previous, I showed one example. I only had the instead bar there. I do not have that in the transmissions bar. Then in that case, which is using this border when you are given that one. Okay, so here we have that in the transmissions bar and there is that in the instead bar, so which is standard, the split-Hopkinson bar. Then you are given that in the a 2 here. That means I do that type of the modeling. Okay, so for the split-Hopkinson bar, actually we have that in here. Initially, we have the stress wave, which is only propagating that into the instead bar. Actually, during this stage, I can actually ignore that's in the rock sample or that's in the transmission bar. Since this, even you calculated that you do not have any of the meaning, this is not stress in there. Okay, if you do not have a power of the GPU, you can specify here. You firstly letting that only calculated this part. So this is what is specified here. And here you can use a bigger of the time step. And you can specify how many of that in the step you wanted to calculate, how many of that in the output and the results there. Okay, after that, you will have the stress wave. When you have that in the stress wave, which will propagate, which is around the rock samples in here, then you will have the rock sample and the transmission bar, which will participate in the calculation. Okay, so then which we're using the time step which we introduced previously. Okay, so that's what is that in here. Okay, I have that in animations here. So this is that before of the stress wave propagating to the rock sample. So after propagating the rock sample, so then we have the output frequency. We make that becomes more frequently so that you get more of the data. Okay, previously we say we will install a strain gauge in the instead bar. Okay, we put in the locations here. Then for the transmissions bar, yeah, we put in that in here. Okay, we say for the impact load, we put in that in a velocity of that in the impact. Okay, so this is that in the velocity. We making that becomes normalized. Normalized, then we give an amplitude. Okay, we using based on one of the laboratory tests. Okay, I visualize that in the next one. So like in here, we have that in the end. We initially fix that boundary, then we put in that in the impact in that in here. Yeah, as we said, before we have the stress wave propagating here, we can initially making that in the time step, which becomes bigger, and the outputting interval is unnecessary for us to put in much of that in intervals there. We can give that in 10 of the thousand, which is special here. But when we have the stress wave propagating to the rock sample, okay, so then we need to change this so that, yeah, so when we needed to use the smaller of the DT, so that's 2 nanoseconds, which we specify that's in there. Okay, we say we were putting that in the impact that's in at here, the impact which is through the boundary condition. So we were getting a velocity boundary. Okay, velocity boundary is which is that we given a waveform like into this. You can see here that's waveform that's normalized. I have maximum 1. That's 1. Then multiple the amplitude. So that will be the actual of the wave. The amplitude, I mentioned that in the previous one, the amplitude, which is about 5 meter, that's in the per second. So that's the amplitude multiple this one. Okay, so then that's the wave which we input in that into here. Okay, so that's the wave. We given that in an additional of that in the input file. Yeah, I will give you this and that in the input file. Okay, so let's look at that in the input file. So the input file, which is I prepare that into here. Okay, so this is actually this is a text file. The format is that how many of the number. The first one is how many of the number in this file. Then this will correspond to each of that in the 10. So what is the amplitude? If we visualize this one, so visualize this one, actually the input of the amplitude, so which will be looks like this. Okay, so then here we prepared that the input in the file. Then I have here that's in the monitor. Yeah, we say we put in 2 of that in the strain gauges here. Then that's we monitor the stress wave in here. So after that monitor, we will have the output of that in the file. Okay, then we have that prepared, that's ready. Then we do the calculation. Okay, so then what we do is that we have the file. Okay, we copy the file which we prepared here. We only needed to, so previously, my lecture, I say you only needed to have these 2 files. So today we have an additional file. This is that to give that the impact. Okay, we copy that. So then you goes into an exe file, which I shared that to you before. Okay, so this is that which I shared that before. Then I copy that into here. Yeah, then after that, so then you can run. Okay, so run. Yeah, like this, given that, okay, we have that in the exe file, which I shared that before. I have instructed you previously many of the times. Okay, we can use in the console to run this. Okay, after that, you run that, which will ask you to give it a name. I say, I will give that in a test. Okay, as I say, that's in the test 0. Giving it a name, then that we're reading that into 2 file, then which we're reading the control file. Okay, so then you will see that's in the program, so that's running. Yeah, you will see that's in the initially, so which is that's in the run, that's in the value of the fast machine. So this is only have that in the incidence bar. Then after that's running a while, I think that's in 13,000 and 800. Let's wait until that's the time. Then which will, yeah, you can see here, then which will become slow. And at this moment, I have the stress wave have not propagated to the rock samples yet. You have that in the rock, which is almost that's 0. So then after the calculation, which we found that's in the result. Okay, so I already completed this calculation. Let me stop into this calculations here. Okay, I have already completed the calculation. They calculated the results, which is here. After the calculation, the result is that we have 2 type of the file. So one of that which will show the joints, and then the other one which will show the element, the solid element. And for this one, I say you are using the parallel view to visualize that. Okay, let me demonstrate how do you, yeah, so parallel view. Okay, so that's the, sorry, so this is that in a 2-dimensional of the Brazilian test. Yeah, instead of that in the 3-dimensional. Yeah, but you can see that's in the stress wave propagating here. Yeah, you can see that's in the stress wave. Okay, I'm making this a little bit smaller. So that's yeah. So if I'm making that, Yeah, you will see that's okay. Anyway, so that's the two-dimensional, but let's look at that in the one which we did that for the three-dimensional of that in the BTS. Okay, three-dimensional, we say we will open the calculated results using the palette view. Okay, so the results, calculated results is here. I will replicate this results as what we did that before for order of the modeling. Okay, we output in these results. Okay, this doesn't show the rock sample. Okay, so then, yeah, so let's show that the Hopkinson bar. Yeah, you can show that the damage as well. Okay, if we show the full model, which makes the rock sample, which is quite small. So let me show the rock sample on this set. Okay, so let me show this, that's in three-dimensional. Okay, you can see that's in the stress wave which propagates. Okay, let me show that in the stress. Okay, here I show that's in the y direction. Yeah, of the stress. Okay, here let me show that's in the y direction of the stress and so as well. And then for the plate, for the bar, I show that's in the y direction of that in stress wave propagate. Okay, so let me go a few of the steps. So for example, I go to the 10 of the steps. Yeah, you will see that's in the stress wave where you propagate in through here. Okay, if I go into 20. Yeah, then you can see that's when we have the stress wave propagating here, which we're loading that in sample. So then the sample we're loaded. Okay, if we further go forward, you will see that's in the further of the stress concentration. Yeah, then achieving that in the balance, then you will see the crack, which is full. Okay, I go that's in the folder. Okay, you will see that's in the crack, which is full, that's in here. Okay, then this procedure, then I goes into the next of the step. So then you will see, yeah, finally that's a fail. Okay, I put in that in the pump handle presentation. Okay, in the pump handle presentation, this is that in early stage. Okay, then the stress wave which will propagate into the sample, which is achieving the dynamic of the stress balance. Okay, then you will have that in the crack, which is full, then which is the sample, which is completely fail. Okay, so besides that, we get in the failure of the pattern. You can also get in the particle size distribution. So after the calculation, so you will see here, which will have a number of that in the, okay, let me show you that's in the folder there. Okay, the folder here. Yeah, you can see here that have the particle size distribution. For each of the step, we can calculate that. And so what is that in particle size? Okay, so let's looking back into the compounded presentation. And here initially, so you will have that in the step only have one of the, since obviously we only consider the particle size distribution of the rock sample. There is no point for you to consider the bar since the bar won't fail. Initially, we only have one object. Okay, so then in the middle, when we have the crack fragmented form, so we have this, that's in 37 of the fragment. And then continue. Okay, if we go into the last step, okay, so let me show you that's in the last step. Okay, you have how many of the fragment this is there. Yeah, so we found that 2,177 of the fragments is there, and each of that, so we delete each of that. Yeah, obviously, so that's irregular. So we given that a nominal of the size, the maximum size or minimum size. So what do we do? Actually, we try to use a rectangle to fit in that the form of the fragment. Yeah, then we give the longest boundary, and that's the shortest boundary. And that's the nominal of the size, which is according to its volume. Yeah, so then divided by that surface area. So then we get that the number of that sets. Okay, so this is the second of that output for you to do the dynamic of that the BTS test. Besides that, okay, so we wanted to hold that the stress wave which is propagate. As we said, we put in a strain gauge in the input bar and another strain gauge on that the a transmissions bar. Okay, so you notice that after that in the calculation, so which were found two files there. Okay, so these two files, okay, let me go back into, okay, so which were found, that's in the two files here, which is one of that which is called the strain at the strain gauge and the stress at the strain gauge. So for this input file, you can open that and using the Excel. Okay, so here that's I open that in the using Excel. Then I using the Excel to draw that in the figure. So that's the figure which I show that in the PowerPoint presentation. And for this one, and you can compare this is the stress wave propagation, what you modeled, and the ways that's in the experimental. Okay, so let's go back into the PowerPoint presentation. Yeah, so what we showed that in the previously, so you notice that in the early stage of my model. So, okay, let me direct you to go into that page. Yeah, so we have this is the comparison. Yeah, so the stress wave compared with the experimental results. Yeah, so that's what it is we getting from the that type of the monitor of that's in the output. Okay, I think that we get that in all of that in the information which we found that in the standard the split-Hopkinson bar dynamic BTS test. So you are getting the fracture pattern, you are getting that in the particle size distribution, and the particle size distribution. So you can draw that particle size distribution either to write a pattern of the script, or you using that in Excel, obviously using Excel each time, which will involve in the repeating of the calculation. So idea of the case is that you writing a code either using C++ or Python or any other of the language, then which will be easy for you to get in the particle size distribution. And then the other one, which is what we usually do, is that we wanted to get in the monitor the stress wave in the impact bar, and that's in the transmissions bar. Okay, I stop in here. I using a little bit, that's the more of the minutes. Okay, so Duan, I handed this back to you.
Okay. Thank you, Professor Liu. It's a very wonderful lecture. Professor Liu gives the introduction of the SPPH-based dynamic 3D gradient test, tensile test, and then give us a case show of how to model the SHPB based 3D Brazilian tensile test. And now we have several minutes to discuss the implication of the important implication of this method and detailed things on the model and the calculation, especially for the students ranging from the geometry, boundary condition, control parameters, calculation, and visualization. And they will give very an important tool to conduct their research associated with dynamic rock mechanics. Yeah. So now anyone who have questions can hands up or ask Professor Liu directly. Yeah.
Yeah, so we can see, so now at this moment, the rock dynamics, so that's the one of the most important topic. And for the rock dynamics, the basic of the experimenter, which is switching Hopkinson bar based on of the test. Yeah, you can see, yeah, through this tutorial, yeah, we can easily to model the one-dimensional switching Hopkinson bar. Yeah, as I introduced a few of that, the extension of the example, yeah, we can easily to model that even more complicatedly involving the grain-based of the modeling, or that's the mostly state of the art of the three-dimensional splitting Hopkinson bar. Yeah, I think that's for the three-dimensional Hopkinson bar. In well, as far as I know, only have two universities are able to do that kind of laboratory test. One of that's Monash University, then the other one is Shenzhen University. Yeah, so I think that's Shenzhen University, which is just starting to do that in the 3D Hopkinson bar. And for one-dimensional Hopkinson bar, I think so now many of the universities, so that's will be able to do that. Yeah, but for us to use the numerical method, yeah, it's easy for us to model either of that in the one-dimensional splitting Hopkinson bar or three-dimensional Hopkinson bar. I think that for you, if you did any of the experimental using you have any of the experimental results, then follow the tutorial, what I introduced here, then using our code to model the experimental what you do. Yeah, I'm sure then you have combined, then yeah, you may be able to publish a very good quality of the journal's paper.
Yeah, I understand that the numerical simulation help us understanding the failure mechanism of different conditions. As usual, the complicated three-point bending and the Brazilian test, tensile test, all these can be done, can be conducted using numerical simulation. Both with the confined compression or biaxial compressor pressure or three-dimensional. Yeah, I also see the spalling. Yeah, that's a very interesting phenomenon, and numerical simulation have understanding the mechanism of this spalling. So I think we can students can have this opportunity to ask to discuss with